let me introduce Mr. Jacques Chivel. You're going to introduce our speaker for this afternoon. Enjoy.
Thank you. So I have the privilege to introduce our next plenary speaker, Owen Casey, who is a world-renowned forensic expert in computer and information security and in digital traces. So I'd like to start to show you a digital trace. The black spots correspond to ones and the white spots to zeros. A digital trace is a silent witness. Let's try to make it talk. Okay. It's hard to maintain the information here. So here we get some information which is not very interesting. I totally agree with our brilliant plenary speaker this morning, Mr. Drow, when he said that actually bias can be introduced when we use context information. But I want to be a little provocative here, and I would say this is a typical example of what we can get sometimes when we don't use contextual information. We get a correct answer, but with no interesting information. So let's keep the same digital trace, and now I want to add some relevant context information. Oh my, it's hard. Hi. So here we recognize Owen Casey. Owen Casey has an extensive experience in investigating and managing complex security breaches, including network intrusion with international scope. He's also the author of the foundational book, Digital Evidence and Computer Crime, and he has been actively involved in digital forensic research since 2000. Currently, he's focusing on automation and artificial intelligence. And last but not least, he just moved a month ago with his family to live in Rome, Italy. But what about the talk itself? For the talk itself, I need another relevant contextual information. Artificial intelligence. Yes, Owen Casey is going to talk about artificial intelligence and automation, the possibilities and the limitation when analyzing digital traces. Owen, the floor is yours.
Trust a digital forensic examiner to use an overhead projector. I think the only one in the conference. Very good. So just a bit more background for the purposes of this talk. I've been an engineer before I became a digital forensic examiner, and I've seen automation and artificial intelligence applied in different contexts. So I have some background in the application and the problems that arise, both technical and social, that I'd like to frame our thinking a bit as we head into an era that I see taking artificial intelligence and automation pretty much to as far as we can imagine it right now in digital forensics. I'm going to focus on digital forensics because that's my area of specialization. I've had over a decade of forensic examination experience in different contexts, criminal, civil, and also data breach investigations. But some of these concepts could also be applied to other forensic disciplines. So just keep that in mind. And also keep in mind that this is an area that artificial intelligence is a fairly broad field. So my exposure is in particular applications. So I'm not an expert in every aspect. So there are many aspects of artificial intelligence that are being actively developed in other areas that I may not have deep knowledge of, but may have some applications. So don't limit your kind of thinking in terms of specific applications to what I present in this talk. You've probably heard repeatedly that in digital forensics, the amount of evidence and the casework is increasing. That's almost a given. And what I want to focus on is something that I find more interesting, and that is that our knowledge and specializations are increasing. What I mean by that is the diversity of the technologies is broadening, where we have different types of computer systems, different smartphone technologies, each with their individual nuances and differences. We also have networks now becoming more involved in our investigations with the cloud, but also within an individual organization with network-attached storage, network logs, network traffic. Each of these areas requires a high degree of technical specialization. And within each of those areas, we have a variety of information that's expanding as well. So you have Windows 7, Microsoft Windows 8 is coming, and each have their own individual differences and artifacts that we have to learn as forensic examiners to interpret that data and reconstruct activities on the computers. So as we get into smartphones, we similarly have different data structures, text messages, call logs that we have to learn about, be able to reconstruct, some geolocation information which has technological nuances. I have some background that I'll pull from in satellite operations, and I'll tell you that GPS tracking and the coordinate location information isn't always precise, especially when you're dealing with smartphone technologies. So there's a lot of technical background in interpreting that data that requires specialized knowledge. We also have the network traffic and logs with individual applications creating different information that we have to become familiar with. So again, more specialization, more knowledge that is distributed among experts. The challenge here is we are currently, in many labs, followed a model of putting people to the task. And what we found is that you have this ineffective use of knowledge. I use this example, it's a bit arcane, but also I think demonstrates the point that if you put more people to this task, it's not going to solve the problem. We see, especially in digital forensics, individuals who develop a specialized set of knowledge will find other opportunities that are more appealing to them, either financially or from an experience standpoint, and they will go leave with that knowledge and leave, say, a forensic lab or an individual group with a deficit, unless that information is captured. So what I want you to be thinking about is the knowledge that we are generating in digital forensics that's becoming a very broad field, different operating systems, different types of information in people's heads right now that some organizations are starting to move to capture that in the form of automation. Now I'm going to talk about some of the general benefits and then also some examples of the shortcomings from my experience. Some are simple, and this is, even if you're an individual forensic examiner or you work in a lab, the efficiency of work and the repeatability and consistency of work is an important factor. So bigger labs are more concerned about it because if you have inefficiencies, they escalate as more cases come in. And so the idea of automation is appealing because it makes things more streamlined, things can be put into a process, and also you run the risk or less risk of an individual examination that's performed by someone who's less experienced coming up with no findings, where a more experienced examiner might look at the same case, the same evidence, and come up with significant findings. So the inconsistencies that can occur across different individuals with different experience levels can be at least smoothed out a bit if you can capture some of the expert knowledge in code, in automated back-end processing. That also has a degree of knowledge capture and knowledge sharing that's very appealing Because if you have an individual who leaves an organization after having developed years of expertise in a particular, say, Microsoft Windows 8 operating system analysis or a specific type of data analysis, if you could capture that before they left, or you're systematically capturing that information in code, they can leave without the deficit occurring in the lab. There's some of that knowledge retained in the automated process. So there's a significant benefit there from an operational standpoint. One of the things that I think it also benefits the analysts, me personally, for example, I've found a benefit that I can focus more on the harder problems from a forensic analysis standpoint, and then some of the new areas of research. So I've, over the years, whenever possible, tried to figure out how to optimize the routine tasks and focus on the more interesting problems and advance our abilities. So if you have the knowledge within our heads and the problem-solving capabilities, and I'd like to examine that phone later. That's my rule. You can have it back. But the general focus of using human skills, human problem solving, to deal with the harder problems and have the routine tasks dealt with in an automated fashion is a goal. It's something that's a goal, I think, that benefits the individuals and it benefits an organization. But there are some pitfalls that we should, I think, benefit from, at least my mistakes. I like to say that I've made a lot of mistakes in my career, and the one reason I teach and come to talk with people is to try and help those who haven't yet made those mistakes avoid them. So that's, I call that experience, or the school of hard knocks. If you can learn from my mistakes, I've achieved my goal. One of the things that I've done over the years is automate myself out of jobs. If I do a good job of capturing my knowledge in some sort of programmatic way, I no longer need to do those routine things. So I'm not saying I get fired. Ideally, it's a move to research and development, more interesting problems. But in essence, there's a personal impact that can occur that we have to take into account. So I use this little, it's nice to, things that we fear personally, it's good to laugh at them, okay? So when you have a degree of, let's say, automation coming into a workplace, you have to consider the impact that that's going to have on the individuals who are being automated, if you will, or whose knowledge is being captured. And that's a significant risk if you don't manage that issue properly. There's a degree of resistance that can occur and a degree of risk in terms of people feeling disenfranchised and leaving. So that's one of the risks that comes with automation. But then there's also the risk of unobserved errors. As processing occurs in the machines that we've programmed to automate our routine tasks, what happens if something goes wrong? The ghost in the machine decides they don't have the intelligence to deal with a particular problem and move past it. How do we know? So that's one risk. I'll talk about how do we mitigate these in a minute. Another is when our primary focus is on capturing our knowledge and looking for ways to automate it, we're looking for the things that we already know. What happens in a case where you enter evidence into an automated system and there are artifacts that we haven't encountered before, or they have features that we haven't really engineered our system for? They won't fit the pigeonholes that we've created, and we may miss information. There may be omissions that occur as a result of our inability to predict those specific types of data coming in, new data, new types of data. So the omission of new data types or previously unseen data types is another risk that we have to guard against. I mentioned the alienation of human analysts, but there's also the risk of increasing our costs. We may make a more efficient operation, but in order to maintain an automated system, we need a different set of expertise. We need people who are automation specialists. And that's, if you think digital forensics is a specialized area, automation and the specialists who engineer automated systems are equally specialized and probably as expensive. So from an economical standpoint, you have to consider that in your in your decision making as well, that you may end up spending more money to begin with to save money in the long run. So a few lessons learned from the School of Hard Knocks. First, e-discovery. It's something that I wouldn't recommend to anybody. But again, this is an experience that I had that is applicable, and it has some useful lessons. The process was, and still is, getting more and more automated. It's one of the areas that has a lot of money to invest in solutions that automate routine tasks, processing large amounts of documents, large amounts of email, and trying to do intelligent searching and matching. The problems that arise are fairly basic. From a digital forensic standpoint, I look at this differently than people who are predominantly in the e-discovery realm, but I think that the same general standards should apply, that we should have some reliability in those systems and accuracy in our results, especially if you're dealing with timeline analysis. So for example, if you're interested in a particular time frame and you want to filter your data and just look at that period of time, you're going to have problems if the tool itself that you're using to automate your initial processing introduces errors, incorrect dates, for example. I've seen this in email processing with a number of e-discovery tools where they'll basically add date timestamps for the current date as they are stripping information up open and processing it. And that creates a problem where you may inadvertently exclude information as you do date time filtering and timeline analysis. You also risk the embedded data within some of the documents that we deal with not being included in some of the filtering and timeline searching. That's just a design flaw, a bug, if you will, or an oversight. But unless we catch these things, we're going to be missing information. And in e-discovery, that can be a fairly significant, there can be significant penalties if one side requests a certain set of documents for a certain time period, and later it turns out that only a subset of that data was produced. And that can result in millions of dollars of sanctions or euro in civil cases, and it has in the past. Also, excluding relevant files is a fairly common problem that has to be handled, but it's common because a lot of data is either unsearchable or encoded in some fashion. If the design of a tool doesn't take that into account, that information is not going to be observed by the end user, which is a human analyst. You're dealing with there, again, a design consideration, but I just want to first, before we're talking about mitigating these things, talk about the problems themselves. And then deduplication is a difficult area where you're trying to reduce the amount of data that people have to look through repeatedly. You don't want to show somebody 5 copies of an email. But there can be over-exclusion if deduplication isn't done correctly. There may be versions of a document, for example, that have minor differences, and you might be interested in a case in seeing what the changes were over time, but if the method used to deduplicate is it doesn't have enough fidelity, is too broad, it might only show you one of those versions, and you lose evidence, essentially. So you lose information in your investigation. So we have to have a human verification component. This is going to be something that I'll hammer home, I hope, throughout this presentation, where there's a degree of validation that the tools are working correctly, but also periodic verification that the results are accurate, correct. From my perspective also in dealing with satellite operations, when in the past I've had the good fortune to be involved with health and safety monitoring of satellites, we had as a goal to routinize some of the tasks, because I was just out of college. I was happy to do night shifts, but if I didn't have to, I would be happy not to do night shifts. If we could automate some of the things that were required on a routine basis to do some automated monitoring of telemetry and make some basic decisions for the health and safety of the satellite. For example, if it pointed at a bright source of light in the sky that could damage a detector in the satellite, you'd want the satellite to take some fairly immediate action to protect itself, close the detector screen so that it didn't burn out. So we started to do basic expert system, rule-based artificial intelligence. And this was in the early 90s. It was fairly primitive in some respects. We've come a long way, but it still was effective for that particular specialized application, where you could look at the data, get some sense of its normal thresholds, and basically make a rule to get this detector to protect itself if it was in danger of being burnt out by a bright light source. And a lot of other expert knowledge that we would have to do in the middle of the night manually before we figured out how to capture that knowledge in a system. The problem was that that was working reasonably well, except for the situations that had never been encountered before. And this is where human expertise is difficult to capture because there's a degree of experience and intuition and perhaps risk-taking. So there was one night when the satellite was unresponsive, silent. Normally we'd be getting a telemetry stream, nothing. The engineer on call came in, looked at ways to try and get the satellite to respond, nothing. So the chief engineer, he had built this system from the bolts, came in the middle of the night, seemed fairly relaxed, which was surprising because everyone else was running around like crazy. Because you talked about several hundred people being out of work in the morning if the satellite didn't come back online. So he came, he looked at what data was available, he talked with some of the other engineers, and he said, reboot it. That's not something necessarily you want to entrust to a machine. When the degree of problem solving that's required, the experience that goes into that, and the impact, the potential risk is very high. So complexity and risk are very high. You want probably a human who has experience with the inner workings of the system to make a decision. He rebooted it, and hallelujah, it came back. So everyone was in work for the rest of the project. So that's, I think, another example of where the human element is critical to incorporate into any automation and artificial intelligence system. So there's several ways that we can go about doing this. We can basically, instead of making, I've purposefully tried to reduce the emphasis on the word automation here, where this is more of an assisted technology. So computer-assisted processing does two things. It puts the human in the driver's seat, so it deals with the social aspect of potentially having a human feel threatened by this replacement, if you will, this system that's supposed to capture their knowledge and perhaps make them dispensable. Instead, the human is in the center of this, and this is technology. It is assisting us as forensic examiners to make decisions. And ultimately, we make decisions that are fairly analytical, fairly, I'd say, difficult problems. We have to come up with ways to test our tools, determine whether the tools are reliable. So there's testing and validation that needs to occur for any automated component to determine whether it's introducing errors or omitting data, so that we understand its behavior and we understand its weaknesses. And there's also an ongoing monitoring that we have to take into account, where we have to have a transparency in the system, a way to look into the processing and figure out if there are errors, so that we don't have these silent errors, these unseen errors. We can look at an audit log, determine that the errors occurred, and we can take some action to address them. And similarly, there needs to be an exception handling process by which, if there's data that couldn't be searched, if it's encoded, it's not searchable in some fashion, or it couldn't be processed, there's some question about it, that needs to be set aside for a human analyst to make a decision about. It can't just be passed over and lost, because then we run into that situation where the new types of data that we encounter may just be missed, may not show up in our evidence. And we also have to enable a deeper level of analysis there, where it's not just the examiner seeing the results of processing, but they can also dig into the details. So go into the data, look at the raw data, and not be essentially distant from it at all times, but be able to go and troubleshoot a problem or verify data at a low level. So there's involvement at all components in the design, the initial testing, and the ongoing monitoring that I'd like to get you to internalize a little bit if you're interested in this area. So I'm going to show you how to read this diagram because I'm going to reuse this model. You can read it like a clock, 12, 1, clockwise, where we have initially a study of our processes. We formalize them and try and essentially develop areas where we understand the process enough that we can automate it. So once we've studied it, broken it out into its components, and we can capture that process, we then can execute it. We create the automated system. And in that automated system, we should have some transparency, the audit logs that enable us to control and monitor it on an ongoing basis for any problems that might be occurring. And as we learn either bugs in the software or we learn new methods that we need to automate or optimize, we get into an analysis mode where we try and continuously improve the system. So that is a continuous effort. You can't just create automation and let it go. There's a cycle of improvement and adjustment that needs to occur. And ultimately, it needs to be human-centric, where we have people being supported, being raised up on this platform, but ultimately being the decision makers, the analysts that control the system and monitor it, improve it, optimize it. And ultimately, we hope that that's going to keep the good people who are working in our labs engaged, will make better use of their time, spend less time doing routine tasks, and develop a system that supports their ability to solve problems, more complex problems. So that's then to my next point, not to separate too much between automation and artificial intelligence, because there's quite a bit of overlap. When you're starting to build an automated system, you're capturing some expertise in it. You're creating an expert system with some rules generally, but let's think about automation separately for a moment. And I've always felt that artificial intelligence is an odd field because the problems that we solve are no longer really worthy of attention, and so they kind of fall off they fall out of the category of artificial intelligence in general. It seems like the unsolved problems that we're trying to solve are the area of research and development in artificial intelligence. But I wanted to just raise your hand if you think that you encounter some form of artificial intelligence in your daily life. I think there's a few hands lifted, but I think more of you encounter it than you know. So some basic applications early on, OCR, optical character recognition, were early implementations. You also have fraud detection is a fairly simple, well, I wouldn't say simple, but fairly common application of an artificial intelligence system that's making decisions, flagging anomalies. There's some rule-based approaches. There's also some statistical analysis that goes into it, depending on the type, whether we're talking about credit card fraud or, say, telephony fraud, for example. So there's technology already out there that we're using and seeing that's somewhat related to forensic investigation. But more related, we have in e-discovery document review, assisted document review that has actually come a long way in terms of natural language processing, basically automating what a legal assistant can do over a large quantity of data and showing, and this was a discussion that we had on LinkedIn, showing better results ultimately than just a human analyst working alone. There's still the need for a human review, but it provides the ability to go through much more data more quickly and come out with relevant matches, relevant hits. And we also have similarity matching, say, of facial features in pictures and video that has application of artificial intelligence. I'm going to talk a bit about some of the lessons learned here, too, where these are great capabilities, but they come with risk. And we have to I think, just be aware, we don't want to stop progress, but we have to make careful progress, thoughtful progress, so that we don't run into a situation where we're overlooking important features or making decisions about our use of the technology that are dangerous. And I smile because one of the questions that came up, I didn't realize what the surprise this morning was going to be, but I was fearful that it might be an embarrassing photograph of me when I was young. So I decided to include it myself in past conferences. But this is, just for discussion purposes, for facial recognition, we've come a long way when it comes to, I wouldn't call it facial recognition, actually I'd prefer to call it facial detection, where if we have a known source, so a picture of a specific individual, whether it be a victim of child exploitation or a terrorist, we have a known source that we want to look through a large quantity of images to find likely matches. The technology has come a long way where it's quite effective and works. Some of the algorithms work with shadow and different angles, but it's not 100% effective. So in one aspect of my work, the question came up as to whether the facial recognition technologies could be used for actual identification of potential targets in military contexts or in, say, child exploitation investigations. And my immediate response was, don't use this information to make a final decision. Don't shoot to kill. Don't use this as 100% accurate, because there's a good chance of false positives. Anyone who I think has seen some of the demonstrations out on the vendor floor or who's worked with this in the past, you know that there's going to be pictures included in a set of apparent matches that clearly are not matches. The poor individual who got ranked first here as perhaps a match to me, I hope no decisions were made based on my behavior and my history. But you have to basically use this as an investigative aid. Again, it's a platform for human analysts to use to focus their efforts. It's not intended to replace the human analyst and make a final decision. And one important thing to consider, and this is just I try and simplify this as much as possible, there are things that we don't know well enough to capture. This is why we have certain things that a human analyst might find in a forensic examination that an automated system or artificial intelligence system will overlook. So even though we talk about artificial intelligence aiding forensic examiners to find more, there's also a risk of it missing certain things that a human analyst could find. So again, that's why the combination of, and where you draw the line, how much human analysis you bring into the equation is going to depend on the context. But I view it as never a full solution. We can't look at every bit and byte in a case in digital media. There's going to be certain data that we just never find. We have, I think at this point, have come to accept that and hope that we can defend that. And at least if a question comes as to whether that contained exculpatory evidence, we can then try and look for particular features that might be exculpatory. But the quantity of data that we're dealing with, we are likely going to be missing some of the information that is contained in that mass of data. So just from the standpoint of artificial intelligence, it's not a full solution, and we have to keep that in mind, as it's not a silver bullet. We have to combine human analysis and also realize that probably there is no silver bullet, there is no full solution. But there is good research out there. I wanted to direct at least some of the work that interests me in this area and direct you to it. There's been some work in cross-drive analysis and multi-agent intelligent analysis that has come out in the past couple of years. One system is MATIC, and it's using a combination of technologies. One of them is my particular area of focus, case-based reasoning, which I'll talk about in a moment, which has great potential in the forensic sciences in terms of artificial intelligence and similarity matching. But they take an interesting approach of some rule-based methods and some prioritization of data to basically make recommendations to a human analyst as to what might be relevant and what probably is not, what could be likely ignored. And as the human analyst interacts with the system learns. So a human analyst can actually say, well, you were wrong, you told me to ignore this is important to my case. They can make that specification, and the system will basically build that into its rules, its weighting of the similarity and prioritization calculations. So that's a system that they started developing in 2009, and it's something they're trying to, I think, refine over time. It's a good proof of concept. Another area, cross-drive forensics, is it's a broader kind of scraping of data across many drives and trying to do some correlation to find links between them. But it demonstrates a good, I think, application of technology to try and deal with large quantities of data to find specific features that might be of interest to an investigation. When I kind of went into artificial intelligence and started to get into the cognitive science aspects of it, my attention was grabbed by case-based reasoning. And I think part of the value from a forensic perspective is that it is designed to take into account cases. So data that's rich in media or text doesn't necessarily have a defined structure, the data that we're commonly encountering in digital investigations. We have to select which features we're going to start using to do our similarity matching, but ultimately it's a more flexible approach than a pure rule-based system. And the way that this works is that with case-based reasoning, you essentially incorporate some knowledge of the experts in terms of structuring what features you're going to start using to do case comparison. You develop similarity metrics and some weighting of those features to see which are more effective to show a match. And when you come with a new case to your system, it will take the features that we've determined are useful for comparison. It will search the case base and come back with cases that are sufficiently similar to perhaps be useful and have solutions. So this is an advantage in our field. When we do a forensic examination, we often generate a report. In most labs, you have to generate a report. So we have solutions. And also the analysis that went into those cases are solutions to specific problems, not just automation problems of how to extract data, but analysis problems of how to interpret data or how to make a more effective use of it. So think about one fairly complex investigation where a forensic analyst spends a lot of time solving a particular problem that could be applied in similar cases in the future, but you can't capture that problem-solving methodology in a just simple automation of the process. It's much more cognitively complex. That's where this more rich feature matching can be useful, and it presents an analyst with possible solutions that they could then adapt to their new case. And once they adapt the solution to their new case, write a report, that gets fed back into the system, and you have a new case solution pair. And you can gradually build up your case base and your solution set. Over time, you have to go back and have a human review and make sure that the system is performing well. And it is probably going to take some adjustment in, are the features that we've selected initially the best features? Are the weights accurate enough that we're getting good matches? So you always would expect, if you present a case that's already in the system to the system, this is a kind of a simple test, that it should find that case, right? It should match, essentially it's identical. So you're doing a quick test of your results, but it should show you whether your system is tuned correctly. So again, this is a different process, but same diagram, general structure of diagram, where we bring in a new case. It's retrieving similar cases from the case base. We can reuse a solution if it's appropriate, and if it is requiring a bit of it, you're never going to have probably the same exact solution, because every case is different, but you can adapt that case solution to your needs, and that gets retained as a new solution in the case database. And you gradually build up your knowledge base. So this is something that's been used in other areas, less romantic or less maybe applicable, less exciting, or help desk call centers, right? of my printer's not working, and is it plugged in? Does it have your toner cartridge? So those are some of the simpler examples, but it's a relatively mature method that's actually based on a bit more research in the learning sciences and cognitive sciences on how the human brain functions and how we actually, as human analysts, find solutions. We look at our past experience. We are basing it on past cases. But this is one thing that I want to say in terms of future possibilities. You might be able to have this system tell you or show an analyst that there's some possible signs of concealment behavior, wiping or encryption, which might be important if you go through an automated system and there's no findings because all the data is encrypted or it's been hidden and your system couldn't see it. Then you might want a human analyst to spend particular attention on that. So it's a flag, essentially, because we're seeing similar concealment behavior to past cases, or common behaviors in certain types of cases, like hackers or child exploitation cases. And then, ideally, we'd have a question-answering system. Did the victim get contacted by the suspect? So you might have some correlation there. Ultimately, and I hope that this doesn't give you all nightmares later, but you'll know the ultimate application of artificial intelligence can come back to get us. We don't want to let it out of our control. But really, I think we should be careful about how much we give out to the machine in terms of control and responsibility. I think what we ultimately want to do here is realize that there are severe limitations and certain applications of artificial intelligence just are not appropriate for certain problems. We recently saw a carving process, a challenge that someone tried to actually every team that competed tried to use machine learning, and it was terrible. The results were far worse than the actual carving methods that we use. So there's also the slow combinatorial explosion of large data sets, the slowness that can be introduced the more data we incorporate. So we have to find better algorithms. And ultimately, there's no human empathy or intuition in these systems. That's where the human comes in. And that's, I've run out of time, but that's the end of my presentation for the most part. But there is a process of kind of a methodology being developed of mitigating these errors that basically you find the sources of problems, you analyze them, you try and address them, and ultimately increase our confidence in the overall result, applying error rates when appropriate. And this is something that's being worked on at the moment. So I'd like to thank you all for bearing with me and hope that was useful.